Hey guys, welcome to the fifth lecture in the Summer Creek High School SNHS lecture series. Today we have our very own treasurer of SNHS presenting, Clay Murphy, please wave. And he's presenting over solar panels and the photovoltaic effect. Before I hand it off to Clay, I just wanted to go through a few things. If you are an SNHS member and you're here and you want your points to be documented properly, please put in your name that you have with us and your school ID number. Also, I just wanted to go ahead and say that this is a school sanctioned event, so please make sure whatever you guys put in chat is school appropriate, like yada yada yada. You guys know the drill. Uh, of course, Clay's lecture was supposed to happen last week, but uh, you guys know what happened last week. Hopefully, you guys stayed warm and your power wasn't out too long, of course. And so this will be pushing our entire lecture schedule behind uh, by a week. So Garv's lecture was originally supposed to happen next week. That'll instead happen the week after. So I think that's about all. I'm gonna go ahead and hand it off to Clay Murphy.
Thank you very much, Justin. So, admittedly, the title of this lecture is a little bit misleading. Really, it should be the photovoltaic effect and solar panels. It's backwards because the photovoltaic effect is, of course, how solar panels work. But it doesn't really have as much of a ring to it when you put it that way, so I put it this way instead. I already got introduced, so I don't really need this slide here, but yeah, my name is Clay. I'm your favorite SNHS treasurer. I'm also the Minister of Enthusiasm and a friend of chemistry. A little background on the topic. I was told a while ago, or I heard rather, and I thought it was interesting that every source of energy generation or electricity generation that we use as humans revolve around finding a way to make a turbine spin, having a magnet on the end of the turbine that uh, is surrounded by a metal coil, generating electricity with electromagnetism. That is all sources except for one, which is solar panels, which operate off of the photovoltaic effect. And I thought, oh, that's neat. And then I didn't think about it ever until a little while ago, taking chemistry, and I thought, I don't actually know how solar panels work besides they make electricity from the sun, but what does that mean? Sure enough, it is much more complicated than that. But I was inspired to do some research and I decided to make that the topic of my lecture. So hopefully, well, I know at least me personally, I learned quite a bit about um, the photovoltaic effect and solar panels through my research, and hopefully I can share that adequately with you guys, and you can learn something as well. If you already know everything about solar panels, then I don't know why you're watching the lecture. You should be the one giving the lecture. So, yeah. Anyway, starting off with the basics, of course. Uh, if solar panels make electricity from light, the biggest questions are, what is light and what is electricity? How are the two things related? Um, Hopefully you guys know this already, but we know that light is made up of discrete quanta of energy, which are called photons. Uh, Photons have various different properties that are of use to different fields of science, but in particular for us, they have a frequency, which is directly proportional to their energy. You can see this equation here, Planck's equation, relates the two via Planck's constant, h. And so the energy of photons is useful when we consider another particle involved here, which is electrons. We know that electricity is the movement of charge, and especially electrons throughout a substance, some kind of material. And we know that electrons are a very common subatomic particle that make up help make up atoms. We have protons and neutrons in the nucleus, electrons floating around in energy shells on the edges of the atom. It is important to note that atoms have several energy levels, not all of which are necessarily filled at one time. Like lithium has, it has 2 energy levels with electrons in it, but electrons can occupy higher energy levels given certain conditions, which we call, well, which they achieve via excitation. Now, the Aufbau principle is very complicated and relates to a lot of subatomic particles, but of interest to us is with regards to electron configuration. The Aufbau principle states that electrons will fill lower energy levels before they start to fill higher energy levels. But that doesn't mean that they have to stay in those lower energy levels. We can move them up. And they do so by absorbing energy through the process of excitation. And now here it says HV rather than E for energy, but of course we know that the two are the same, E equals HV, right? So the pinnacle of science, in my opinion, is considering what happens when we take one thing and we throw it at another thing. So what happens if we get a photon and we throw it at an electron just to see what happens? Well, we know that photons have energy, and we know that electrons are arranged in energy levels. So if the photon has just the right amount of energy, it will be absorbed by the electron, and the electron will be promoted to a higher energy level. Since it now has more energy, it goes to a higher energy level. That's why they're called energy levels. And then the opposite process can also occur when the electron falls from its excited energy level to its ground state. It then releases an equivalent amount of energy in the form of a photon, relaxation rather than excitation. But so a solid relationship now between light and electricity. This is an important basis for how solar panels work, as you might imagine. It's also the basis behind flame test labs, which you've probably done before if you're watching this lecture, by giving energy to electrons. In flame test lab, it's of course energy, thermal energy from the fire, is nonetheless enough to excite electrons, and then upon relaxation, they release photons with a particular amount of energy based on how many energy levels they may have skipped down, and depending on the atom or ion, metal cation generally, that the electron is in the energy level of. And so by observing the color of the flame, which is based on the wavelength of light, which is based on the energy of the photons that are released, we can make pretty good predictions about, well, we can calculate the energy of the photon, and we can make good predictions about what metal cations might be present in the flame test. But that's not about solar panels, so let's move on. Now, another concept that's pretty useful for understanding solar panels is that, well, it's also regarding electron position in relation to the nucleus of atoms. In chemistry, we generally talk about valence electrons, electrons in the outermost occupied energy level. But upon excitation, electrons can also move to another kind of area, you could say, the conduction band. Energy levels where the electron is not so freely, or not freely rather, where the electron is not so strictly bound to its atom and it can move around as it pleases. We know that electricity is the movement of charge carriers like electrons. So when an electron is in this conduction band and it's free to move around, well, then the substance which has the electrons is a good conductor since it can move electrons around. That is the definition of electricity, charge moving around. So we have a diagram of position of valence bands and conduction bands for various materials. On the left, metals. And keep in mind that the vertical axis of this graph is measuring the energy of electrons. Conduction band has, or electrons in the conduction band have higher energy than electrons in the valence shell or in core shells of a species, chemical species. So with regards to metal, we see that there's a large overlap between valence shells and the conduction band, meaning that there is little or no energy required to shift electrons up from valence band to the conduction band, which is closely related to the sea of electrons model that you've probably heard of, definitely heard of if you're listening to this lecture, which describes metallic bonding distinct from ionic or covalent bonding because the metal atoms get together, shed their valence electrons by moving them from the valence shell to a conduction band, where they're then free to move around between all of the cations and hold them together, but also conduct electricity because they can move so freely. We see on the opposite end of the diagram, you have insulators. Metals, of course, are the most well-known conductor, but insulators are quite the opposite, where we have a large energy gap between electrons in the valence shell and the conduction band. The distance between the highest energy valence shell and the lowest energy required for the conduction band, that gap is called the band gap, of use in materials engineering we'll get to that later, never mind. And the dotted line on this graph is the Fermi level, which is the energy of electrons, energy of electrons in the highest occupied energy level of substance at absolute zero, right? 0 Kelvin. So it's just a baseline for measuring electron energy. But so insulators, the reason that insulators aren't good conductors of electricity is because it takes so much energy to move electrons from the valence band to the conduction band so that they can start moving around the substance. Whereas metals are good conductors because it takes no energy or very little to move electrons into the conduction band and have them start being able to move around. Now, somewhere in between is a substance a category of substances very useful for solar panels and lots of electronic applications. That being semiconductors, which are, kind of good at conducting electricity. They have a smaller band gap than insulators, but not as good as metals, which might seem like a bad thing, but we can, with a variety of methods, we can alter the conductivity of a semiconductor at will, which is, in some cases, more desirable than just having something that's really conductive all the time. That's what the next slide's about, semiconductors. So quite a few elements serve as good semiconductors. I highlighted them on this periodic table. Antimony, arsenic, boron, carbon, germanium, selenium, silicon, sulfur, and tellurium. Carbon is a semiconductor sometimes and not other times. We'll get to that later. But you'll notice that of all of these elemental semiconductors, 3 of which, carbon, silicon, germanium, are easily recognizable as being tetravalent. They have 4 valence electrons in a neutral atom. This is particularly a useful quality for semiconductors because it allows the atoms to form a bunch of covalent bonds with surrounding atoms and form a, what's the word I'm looking for? An unbroken crystal structure such that electrons can move throughout the entire structure freely, versus something like a molecular solid, like, well, let's compare, for example, silicon versus silicon, well, versus, I don't know, an organic molecule like carbon dioxide. Ignoring, band gap things, why would silicon be a better conductor than an organic molecular compound? Because in a network solid, like something formed by silicon atoms, there is an entire crystal structure through which electrons can navigate, which means that we can create structures through which we know charge carriers, rather, and therefore electricity can get from here to there, versus in molecular solid, there's nowhere for the electron to go, right? If you look at a carbon dioxide molecule, maybe there's like 3 atoms that the electron can move around, but nothing else. We can't make a wire out of that, or whatever. So tetravalence is a property of a lot of semiconductors because they tend to form network solids. But not all semiconductors, like the ones listed here even, not all of them are tetravalent. Before I move on, carbon. Since carbon tends to form, we know carbon forms several different allotropes, some of which are semiconductors, some of which are not. I won't go into that, but it is considered a semiconductor by some, at least, and it is in some forms. But not all of these are semiconductors in their pure forms. Not all of them are tetravalent, because most semiconductors are a product of the doping process, through which we get a pure substance like silicon network, and we introduce small quantities of some other atom. 2 examples here. On the left, we have introduced a phosphorus atom, which, going back to the periodic table, if you don't have yours memorized, phosphorus has 5 valence electrons. It's pentavalent rather than tetravalent. So if we take out a silicon and throw in a phosphorus, well, 4 of its valence electrons, 4 of the phosphorus's electrons, can form covalent bonds with nearby silicon atoms, but then we have 1 left over that doesn't have anywhere to go to bond. So what does that do? Well, now we have an extra electron that we can elevate from the valence shell to the conduction band such that it can move around the network and conduct electricity. Getting pure silicon versus pure silicon with just, impure silicon with just a very small quantity of a dopant like phosphorus can increase the conductivity massively. And so it's very important that we, in the process of making electrical parts, dope semiconductors to increase conductivity, which is generally desirable. But beyond adding in species with extra electrons, we can somewhat counterintuitively maybe add in species with less valence electrons, actually. So on the right, instead of adding in phosphorus, we've added in a boron atom, which has 3 valence electrons. So we form 3 bonds with nearby silicon, and then we have 1 lone electron that's just sitting there, I guess. It's not a complete bond, right? So what happens? Well, let's say that one of the boron's electrons decides to move from its current bond over to complete bond in the other location. Let's say the top electron of this boron moves over to the right and forms a bond there. Well, now we've completed the bond, but now we've just created another gap up top, right, where we still only have one electron. Nothing has really changed. So we have to understand that electrons are carrying charge around when we talk about electricity, but you can also kind of theoretically think of the lack of an electron as a charge carrier, an electron hole, which instead of having a negative charge like an electron, since an electron hole is the lack of an electron, it has a positive charge. So you can, this is really weird to me, it's kind of jarring, but we can say that by adding in a boron atom rather than a phosphorus and doping the semiconductor, whereas with the phosphorus we added an electron as a charge carrier, when we added the boron we actually added an electron hole as a charge carrier. I think that's kind of funny and really weird, but I think it ties into the measuring current with the flow of electrons versus with conventional current. Electrons we know have a negative charge, but before we knew that electrons were the primary charge carrier, we scientists thought of current as traveling from positive to negative rather than negative to positive. So if we consider a theoretical charge carrier with a positive charge, that would be the lack of an electron. And so we can, movement of electrons, that's current, but the movement of the lack of electrons represents then conventional current, the movement of positive charge. And so when we dope a semiconductor to introduce free electrons, we create what we call an N-type semiconductor. And so N-type dopants would be phosphorus, antimony, arsenic. A few examples. If we dope a semiconductor to introduce holes, then we create a P-type semiconductor. Boron is one dopant, aluminum, gallium as well. A lot of N-type dopants are pentavalent. A lot of P-type are trivalent. Makes sense, right? And another thing with holes is that we can consider them kind of a particle, if you want to think of it that way, with a positive charge. But it's also just, if you track the movement of the electron, like when we, earlier example, if we move the boron's electron from the top bond to the right bond, the electron has moved from top to right. It's moved down and to the right. But when we closed this hole, we made a new one, which was located up and to the left of the old one. So if we focus on the hole, we say that the hole has moved up and right, but that's the same as saying that an electron has just moved down and right. Wait, did I say right earlier? I meant to say that the hole has moved up and left. The electron has moved down and right. So it's strange because you can think of it, you can think of a hole as a charge carrier, or you can just think of it in terms of by introducing a gap, you still allow for mobility of electrons. And so electrons are still really the charge carrier, they're still moving around, and they move in the opposite direction of the way that the holes move. It's so weird to talk about holes moving, it's not how things work. But anyway, so again, let's just take the two semiconductors that we've just created, the N-type and the P-type, and throw them together and see what happens. We get the aptly named P-N junction, which is not only the basis of photovoltaic cells, but also of diodes and transistors, which I don't know enough about to talk about, but I think that's kind of interesting at least. And if you've heard of NPN versus PNP transistors, the N and P do indeed stand for the type of semiconductors used in their construction and the arrangement of them. But anyway, So the p-n junction we have here, we have the n-type semiconductor on the right, p-type on the left. In the middle, we have this depletion zone, which is a little weird, but let's start from the beginning. We take the n-type and we take the p-type and we put them together. Now the n-type semiconductor we've introduced more free electrons to it than it would otherwise have. And some of those free electrons we're going to, spoiler alert, we're going to end up relying on photons from the sun to free up. But some of them will be freed up just by, ambient thermal energy. If we go back to the conduction band diagram, remember that the Fermi level is the energy of an electron in the highest occupied energy shell at absolute zero. But, I mean, we never work with absolute zero. We're always above that temperature. Especially in Texas, if you were a solar panel, I'd imagine your temperature would be quite above absolute zero. So some of the electrons in the n-type semiconductor will have enough energy to move from the valence shell to conduction band and become mobile. And with the p-type semiconductor, something similar, with electrons moving around to fill in holes versus electrons just moving around. And so what we have is that electrons can jump from the n-type to the p-type semiconductor at the junction, the point of contact where they meet. And by doing so, we've now reduced the total number of electrons in the n-type semiconductor by 1, and we've increased the amount of electrons in the p-type semiconductor structure by 1. But we haven't changed the number of protons in either, so by necessity, we're creating some ions here. We end up with cations. Every time an electron jumps from the n-type to the p-type semiconductor, we end up with a cation on the n-type and an anion on the p-type. And so by the pre-existing mobile electrons in the conduction band jumping from n to p, we end up with this depletion zone at the point of contact, the junction, where we have essentially a wall of ions where no more charge carriers exist. They're concentrated in the rest of the semiconductors, but not close to the meeting point between the two. And so now, if an electron tries to jump from n to p, it won't be able to, because we have these static charges due to the ions, positive on the n-type semiconductor, negative on the p-type. And static charges, that makes an electric field. If we look at Coulomb's law, as electrons, which are negatively charged, approach the depletion zone from the n-type semiconductor, they're attracted to these cations on their own semiconductor, but as they continue to approach the depletion zone, they are repelled by the anions there, the negatively charged ions on the p-type semiconductor. So once enough electrons have been exchanged, no more will be able to move from n to p, from the n-type to the p-type semiconductor directly, at least, because of all the static charges in the depletion zone. Creates an electric field. Now, if we wire it up to a circuit, we put a wire on one side and hook it up to a wire on the other side, interesting things can happen. So now let's take our p-n junction and put it outside in the sun. Well, we already talked about what happens when we throw light at an electron, right? And the sun tends to throw a lot of light at the Earth. So we get photons, which, if they have the proper amount of energy, just enough, same amount of energy as the difference between the energy levels that the electron have to jump. The photon with that much energy hits an electron. The electron absorbs that energy, moves from the valence shell to the conductance band, and now can move freely throughout its semiconductor. Previously, we had some electrons that were able to do that anyway by absorbing thermal energy, but we can get a lot more mobile electrons in the conduction band by exposing them to photons from a source like the sun. So when we do this, we free up electrons. This is photogeneration. Photogeneration, process of well, light, right? Photons generating new charge carriers by by exciting electrons from the valence shell to the conduction band in a substance. And so let me go back to the p-n junction diagram. When we get electrons appearing on the n-type semiconductor, we technically get holes appearing then in the p-type semiconductor. I'm just going to focus on the electrons for now. Now you would think that since the n-type semiconductor started out with an excess of electrons and the p-type with a deficiency, you would think that electrons would would move over from the n-type to the p-type after photogeneration. But again, we still have the depletion zone in the middle of in between the two semiconductors, so the electron can't just a newly photogenerated mobile electron can't just move straight from N to P semiconductor. It has to find some alternate route because of the electric field that was already generated by static charges that were created due to ionization from electrons that were already elevated from the valence shell to the conduction band by ambient thermal energy. That's a mouthful. So you'd think electrons would go from N to P, but they actually can't. They end up flooding into the N-type semiconductor, holes into the P-type. And now, so since we have static charges, the depletion zone in between semiconductors, well, there's an electric field there with all these new electrons trying to move around. That electric field per Coulomb's law, it exerts a force on the electrons, which is the electromotive force, which is voltage. Now the electrons, we have a lot more free electrons and they have reason to start moving around. There's an electric potential. And so as electrons start to move, and again, if we have something like this, maybe not with the voltage source, but electrons can move from the N-type semiconductor into a wire through something, and then over to the P-type. Well, if we have the movement of electrons, and electrons are a charge carrier, then we have the movement of charge, and that's electric current. So, yay, we finally done it. We've now generated current through sunlight and some semiconductor magic. This is the photovoltaic effect, generation of voltage and current through sunlight with the help of electrons. I can't help smiling. This is just really cool to me. I'm sorry. But that's not the only part of a photovoltaic cell, of course. Solar panel, there's more. So the semiconductor does, it's been doped to improve its conductivity. But after we have generated all these free electrons and they start moving around, there's not much reason to keep them in a semiconductor, right? We might as well move them into something more conductive so they can move to other things to power, what you do with electricity, light bulbs and stuff. So you have a front and a back contact on the solar panel, which are made of not special semiconductor stuff, it's just metal because it's conductive. And so these take the electrons and, after they've been moved around, the contacts effectively pick up the electrons and move them to wherever they need to go via a wire or whatever. And since we are relying on electrons absorbing photons for this whole thing to work, it wouldn't do very well if the solar panel was particularly reflective and all the photons just bounced off and nothing ever got absorbed. So we have an anti-reflective coating put on the front of the solar panel to encourage the absorption of photons by the electrons. And so that improves efficiency and allows for less photons to be lost due to reflection. But nothing is without its flaws, of course. There are still quite a few things that we could improve on with solar panels. Limitations in the photovoltaic effect itself, among other things. And so if we look at, when we talked about band gap already with moving to the conduction band, moving electrons to the conduction band. But as well, different substances have different band gaps, but the size of the band gap also it plays into what sort of photons can be absorbed by the substance to generate free electrons, to excite the electrons. And so if silicon has a band gap of 1.12 electron volts, I have no idea if that's true or not, but let's say it is. Then if we look at an EM spectrum of light and compare wavelength and energy, we see that we have to, for an electron to be excited, then it has to absorb at least 1.12 electron volts of energy from a photon. If a photon hits the electron and it doesn't have that much energy, then the electron doesn't get excited. We don't end up with any more mobile charge carriers. Nothing happens. The energy actually gets absorbed as thermal energy, which is bad in the long run. We generally don't want things heating up if they don't have to, right? But we see that, excuse me, light, of course, has different wavelengths, and different wavelengths contain photons of varying energies. But we have to generate the most mobile charge carriers, each photon needs to have at least 1.12 electron volts to sufficiently excite an electron. But if we have light that, infrared light is wavelength between 1 millimeter and 700 nanometers, which corresponds to this much energy. The top range of this, 1.77 electron volts, that is greater than the band gap of silicon, so that would be able to excite electrons, but not all infrared photons have small enough wavelength and high enough energy to be able to excite all electrons. Some infrared photons will just be absorbed as thermal energy, won't produce any any charge carriers, and will ultimately degrade the solar cell due to just accumulation of heat. The temperature goes up and problems occur when things get hot. And in addition, the temperature of semiconductors can actually mess with the band gap, and so it's kind of a vicious cycle. I'm not entirely sure how it works, but the more heat that semiconductors absorb, sometimes that makes them function just more poorly than they did before, that they would at a lower temperature. In addition, not all charge carriers that are propelled by the voltage created in the depletion zone, not all of them have enough of a kick behind them, enough force behind them to make it all the way to the conductive contacts on the front and the back of the panel. And so not all charge carriers end up, traveling the circuit and actually moving charge around. So that's lost electricity there. As I've already said, different materials have different band gaps. You might think that having a smaller band gap would be better because that would allow you to, well, not you, you're not the one absorbing energy, you would think that a semiconductor with a smaller band gap would be better because the semiconductor then could absorb energy of uh, longer wavelengths, or sorry, could absorb photons of longer wavelengths uh, with less energy, and it would still be enough to excite electrons into the conduction band. But actually, there's quite a few, let me restart. Semiconductors with higher or with wider band gaps are actually preferred in some cases due to the aforementioned finagling that occurs with regards to temperature and band gap and conductivity. So silicon is a very common semiconductor. I'm sure you've heard of it once or twice. But there are quite a few alternatives like gallium arsenide, or sorry, gallium, that's not an element, gallium arsenide. The difference is, of course, that silicon is generally, well, not generally, it is, it's cheaper and often easier to manufacture into doped semiconductors that we need to make photovoltaic cells. Gallium arsenide, on the other hand, I believe it does have a wider band gap, but it functions better with temperature fluctuations. And the main problem is just that, and this is, I think, one of the biggest problems with photovoltaic cells, is that it's rather expensive. It's a pretty intensive process to synthesize it in a form that we can then turn into semiconductors and photovoltaic cells. And so in many cases, it's cheaper and it's easier to use silicon, which doesn't perform as well, but can have everything, I guess. And those are just two semiconductors. There's a lot out there, and they all have different uses and band gaps, restrictions, pros, cons, whatever. With silicon in particular, but with other semiconductors as well, we have the option of creating monocrystalline or polycrystalline cells, or semiconductors rather. If we have a polycrystalline cell, and that's like if we just got a bunch of silicon, melted it, poured it into a mold, and then let it harden into a solid again, and then made semiconductor out of that. It works, it's cheap, it's easy, but it's not quite as good of a, I believe it has worse conductive properties versus monocrystalline, where the silicon is left as, let me restart. The silicon is layered on top of itself slowly over time. It's a time-consuming process. It's a precise process. It's an expensive process, similar to the synthesis of stuff like gallium arsenide. And so, although it is more effective as a semiconductor in photovoltaic cells, it's also more expensive. And until we can figure out a way to make production less exhaustive, polycrystalline cells are still used quite a bit. We also have the option of using cells with multiple p-n junctions. And the idea is that if you have multiple, you can have photons that don't get absorbed by the first junction, get absorbed by the second, or the third, or whatever. Or you can use substances that have different band gaps to see, excuse me, or you can use substances that absorb light that the other semiconductors wouldn't. So more photons absorbed in the long run, or overall rather. So more mobile charge carriers, more potential for current. Yeah. So, well, again, this is mostly just the chemical and, well, I say chemical as in relating to chemistry. The chemistry background, and I guess physics background, if you consider that, of solar panels, not so much the macro aspects. So I'll leave the flaws and all here. But that does bring us, oh, sorry, I didn't include this for the band gap diagram or graph. In case you couldn't see it on this slide, you can read it here a little more clearly. And then I forgot to use it. What a bozo I am. Anyway, that is the end of the presentation. If you have any questions, you can contact me through the SNHS GroupMe. You can shoot me an email, my school email or my personal. If you go through school email, just make sure that you send the email from a school email as well, otherwise it'll get blocked and I won't receive it. If you'd like to look at the sources I've used, which are down here, all of you were excited. If you'd like to take a closer look at any of these, again, you can email me and I'll send you the slideshow if you'd like to click on all these links. Maybe it sounds like a way to spend an afternoon. I do have to thank Slides Carnival. I am obligated to do this actually. They created the slideshow layout, the graphics, I should say. Overall, it was a pretty decent experience. I'd say like 6.5 out of 10 maybe. No, actually, I'll say 7 out of 10. 7 out of 10 for Slides Carnival. If you need to make a presentation, you can think about them maybe. But if there are any questions, I will sit here and answer them. Otherwise,
looking at the
that is
chat.
the end of the presentation.
Looking at the chat, I don't think. Oh,
a question?
there is not a question.
There's not a question? You just got my hopes up?
Yes.
Dang.
But there are no questions in chat. Please, if you do have a question, you have like 15 seconds to put it in right now. Clay will continue to stare awkwardly at the camera as we wait.
I'm not staring awkwardly, I'm staring normally. This is how normal people stare, Justin.
Alright. I guess there are no questions. So that concludes Clay Murphy's lecture. Thank you guys for tuning in. Of course, if you guys have did not remember to put in your ID number, you guys can go ahead and do that now. Our next lecture is exactly 2 weeks from today at the same time, 6 p.m. Hopefully you guys will tune in for that one. Bye everybody.
Thanks everyone.